Hi again, everyone. So today we are going to be discussing section 4.5, derivatives and the shape of a graph. So I mentioned in the last lecture that maxima and minima are a very important concept to understand, and how to obtain them is very important. And that in future discussions, we would kind of go over how to determine if something was a maximum or a minimum, and even various other things. And so that's kind of what today is going to be. We're going to learn how to identify which critical points are maximums and minimums and maybe neither. And we're going to discuss other aspects of a graph that you may not even realize existed. Um, so let's first take a look at these two ideas. So we have this idea that we could be increasing, but kind of in two different ways. So both of these functions are increasing functions, and we remember from that one theorem that increasing means your derivative is just greater than zero. So we have this that kind of has like this upward look, and then this which kind of has a downward look. And they're both increasing functions, but the shape of this graph is really important for something that we'll be discussing later on today. Same idea with decreasing. So we have this decreasing that looks like a downward decreasing, and then we have a decreasing that's a little bit more of like an upward decreasing. And those are going to be very important. And we remember decreasing means your first derivative is less than zero. This is, again, a little refresher about exactly what it is that we could be looking at. So we could have local maximums, local minimums, absolute maximums and minimums, and then you could also have something that could be uh, undefined. So this kind of a cusp looking thing. So as we see from here to here, we are increasing, which means that our first derivative is positive. But from A to B, we are decreasing, which means our first derivative is negative. Because this is a local minimum, we know that our first derivative is zero there. From B to C, we see that we are increasing because we remember we read the graph from left to right, which means our first derivative is positive. And here this is kind of a weird looking spot. I don't know if I would call this a maximum or a minimum. This is just kind of some kind of a horizontal tangent line where our first derivative is zero. And you would notice once we get to this idea a little bit later on, that we see we go from increasing to increasing. And if you just kind of think about it logically, a maximum would occur when you go from increasing to decreasing, and a minimum would go from decreasing to increasing. So if you go from increasing to increasing, you're not turning in any way, so you're not achieving a maximum or a minimum of any sort. And so this is just some strange point. We increase until D, where we see another horizontal tangent, which indicates that this here is a maximum. And in fact, it looks like the absolute maximum of the graph. And then from here on out, we are decreasing, which means our first derivative is negative. And so this is something that we're going to kind of be taking throughout the rest of not only this section, but future sections. I believe 4.6 as well. You'll notice we skipped 4.4. That one isn't something that we want to discuss. So let's get a formal definition. We already kind of vaguely understand this concept. Like I said, if you go from increasing to decreasing, you're a maximum, and decreasing to increasing, you're a minimum. And that's just kind of intuitively, it makes sense, right? So if you have a continuous function over some interval, it could be negative infinity to positive infinity, doesn't matter. If f is differentiable, except maybe at a point C, which could be like a cusp, then f of c can satisfy one of the following descriptions. So if f prime changes from positive to negative, then f of c is a local maximum. So if we are looking at a first derivative and we see we go from positive to negative, we know it's a maximum. So this is how we can tell from first derivatives what is a positive, what's a maximum and what is a minimum without knowing the shape of the graph. If f prime changes from negative to positive, then f is a local minimum. If it has the same sign, then it's neither a maximum or a minimum. It's just kind of a point on the graph. So this is going to be a very, very, very important concept that we're going to be using quite a bit from here on out. All right, so how can we use the first derivative test? I think it's pretty self-explanatory, but this is my method to doing this that just kind of makes it a little bit easier. So let's consider a function that's continuous. Step one, find all critical points of f. We remember the critical points are taking the first derivative and setting it equal to 0. All right, find the values. Step two says put those values on a number line labeled f prime of x and plug in points between those critical points. Put a plus if it's positive and a negative if it's negative over that interval. And we're plugging it back into the first derivative function. Step three is use sign analysis to determine the maximums and minimums based on increasing and decreasing, right? So if it goes from plus to minus, then we're increasing to decreasing, which tells us that we have a maximum. If we go from minus to plus, we're decreasing to increasing, so we have a minimum. If we go minus to minus, it's just a random critical point that doesn't tell us anything. All right, so let's go ahead and try an example. So use the first derivative test to find the location of all extrema for this function here. We aren't going to use a graphing utility to confirm. You can use that and confirm if you'd like, but we're not going to do that. So we have this function. Let's go ahead and first, well, it'd help if I didn't draw it with a highlighter. I swear, one of these days I'll get it. Maybe not. Maybe I'm lying to you. Okay. Let's take the derivative. F prime of x equals, so the derivative is 3x squared minus 6x minus 9. So we know in order to use the first derivative test, we have to set this equal to 0. So 3x squared minus 6x minus 9 equals 0. But I don't want to factor something with a 3 in front. I notice that every single term here has a 3 in it. So I'm going to divide everything by 3. If I divide everything by 3, 0 divided by 3 is 0, so we're good over there. What I get is x squared minus 6 divided by 3 is 2. X minus 3 equals 0. And now we can factor this using our regular technique. So I need two numbers that multiply to negative 3 and add to negative 2. So I can do maybe x minus 3, x plus 1 equals 0. And what we get is that x equals 3 and x equals negative 1 are going to be our two critical points. All right, and we're looking for local extrema, and so we're looking to find if they're maximums or minimums. So now we're going to use this idea of a number line. So we found our local extrema. We don't necessarily care where they are in terms of the y value. All we care about is the x value. So we're going to take our number line, label it that this is the first derivative number line, and we are going to plug in these 2 points. So here's negative 1, here's 3. And what we're going to do is something called testing points. So I want to find in each interval, so from negative infinity up to negative 1, not including, because we know if we plug in negative 1 into our first derivative, we'll just get 0. We want to know, is it positive or negative? And that tells us if it's increasing or decreasing on our original function. We'll plug in something in this interval and this interval. So we want to plug in some number. We get to choose which number it is in every single interval we have to determine whether the original function is increasing or decreasing. So less than negative 1, I will choose negative 2. So f of negative 2, I often get asked, how did I choose that number? So I knew that it had to be something less than negative 1 because I need something in this interval here. I just chose the closest number to negative 1 because it's a small number and it's a little bit easier to compute. But if you wanted to choose like negative 100, you could do that too. It's really up to you. You can't choose negative 1, but you can choose negative 1.5 if you want. You can choose whatever value as long as it is in this interval. So f of negative 2, if you plug negative 2 into your first derivative function, we would plug it into kind of any of these would work, to be honest. So plug this in, we get negative 15. Oh, I apologize. We get positive 15. I try to write down all my solutions beforehand so that I don't bore you by plugging it in and wasting your time. So f of negative 2 is positive 15, and so I'm going to indicate that by putting a plus sign here. And what that tells us, I can also write that this means that our function is increasing. Now I'm going to choose a number between negative 1 and 3. My suggestion is if you ever have 0 in your interval, choose 0. It's really easy. F of 0, because all you have to do is plug 0 into your derivative function and you get negative 9. So we know that's negative, which means that your original function is going to be a decreasing function. The last one, I need to choose something greater than 3, so I'll choose 4. When I choose 4, I get positive 15 again, which does not always happen. Plus, so I know this is increasing. So now I can go ahead and determine what's happening at these 2 points. At -1, we go from increasing to decreasing. So we go from increasing to decreasing, which tells us that we have a maximum. So x equals -1 is a maximum. X equals 3 goes from decreasing to increasing, decreasing, increasing. We see that means that it's a minimum, is a minimum. All right, and that's all we're being asked for, is to find the location of the local extrema. And location in this case is referring to the x value location. All right, let's go ahead and try another one now. So find all local extrema of f of x equals 1/4 x to the fourth plus 4/3 x cubed minus a half x minus 4x plus 5. This looks kind of crazy, but we can go ahead and take the derivative and it'll work out nicely. So again, we'll start off by taking the derivative of our function. 4 times 1/4 is just 1, so we get x cubed. 3 times 4/3 is just 4, so this is plus 4x squared. 1/2 times 2 is just 1, so that's minus x. And then the derivative of minus 4 is just minus 4, and the derivative of 5 goes away. So that's not too bad. If we factor this function, what we get is, I will tell you the factors go x minus 1, x plus 1, x plus 4. And you can do that by factoring by grouping here if you'd like. You can group these two terms, and then factor them. So you factor it, and we know we have to set this equal to 0 and solve. So that tells us that x equals 1, x equals -1, and x equals -4 are going to be our critical points or critical numbers. Again, we use those terms synonymously. So these are going to be our critical points. But we're looking to find the local extrema, so we don't necessarily care that these are the critical points yet. What we care about is, are they local mins or local maxes, or what are they? So let's go ahead and determine that. So again, what we're going to want to do is we're going to want to draw a number line, and we're going to want to plot those values on the number line. So we can have -4, -1, and 1. So what you notice is now we have 1, 2, 3, 4 intervals we're going to have to test points in. So I'll go f prime of something less than -4. So I will choose -5. When you plug -5 into this right here, I suggest plugging it into the factored form as long as you know your factors are correct, because it's a little bit easier to see whether your function is going to be positive or negative. The actual number does not matter in the slightest. So you don't actually have to come up with a number if you can come up with a sign. So what I mean is, if you plug -5 in, -5 minus 1 is going to be negative, -5 plus 1 is negative, negative times negative is positive, -5 plus 4 is going to be negative. Negative times positive is negative. So I know this function is going to be negative already. So I can just go ahead and put a negative right there and call it a day. Now, if you actually did the computation, you'd get that this is going to be -24. And you would confirm that you do, in fact, have a negative number. But again, -24 just tells you that the slope at that point is going to be -24, but we're not graphing that, so it doesn't actually matter. In no world are going to be able to accurately get a slope of -24, so it's fine. Anytime you're asked to actually graph something, it's going to be sketch. And if it vaguely looks like this shape, then you're good to go. As long as everything kind of checks out in terms of in this interval, it's supposed to look like this, and this interval is supposed to look like this, you're good to go. If it doesn't hit all of the y value requirements, I expect it not to. Mine don't even look like that. All right, so we'll choose something in here. I, again, want to choose kind of a smaller number just because it'll make computations a little bit easier. So maybe -2, f prime of -2 equals, and again, if you don't want to actually compute it, you can just go ahead and see if you would get a positive or a negative number. What you get is a +6. So I can go ahead and put a plus right there. I can choose something else in this interval now. Again, I can always just choose 0. So plugging in 0 means you're just left with the constant. So that's obviously a very easy choice. You just get -4, just tells us we are negative here. And then I can say f prime of, choose a number that's over here. 2. Sure, maybe 2. You know what? Let's make it even more fun. What about 5? You can choose literally any number that you want. If you choose 5, you plug 5 in, you get positive 216. And so that really just tells you again that you absolutely do not want to be trying to graph these slopes. Have fun trying to graph a slope of 216. All it tells you that is that it's positive. So this says we are decreasing here, increasing here, decreasing here, increasing here. And what that tells you is that at x equals -4, from decreasing to increasing, you have a minimum. At x equals -1, increasing to decreasing, you have a maximum. And at x equals 1, decreasing to increasing gives you a minimum. And that's exactly what we're looking for. All right, now we can talk about this idea that I kind of hinted at earlier, that it matters whether it looks like an upward increasing, upward decreasing, and the same when it comes to increasing, right? So now we have this idea of concavity. And maybe you've heard this term with other things. Maybe you've never heard of this term before. So concavity deals with the shape of the graph. So for an increasing function, this is actually, these are wrong. I got these off of the textbook, I believe. This is actually incorrect. If you look, this is a decreasing function, clearly. So I'm going to fix that. I did not make this diagram. So this is decreasing, obviously. We can just use some common sense to say that it's decreasing there. This is increasing, this is decreasing. So that's correct. This is not correct. This is going to be increasing. Okay, now that we have the correct information, so this is a decreasing concave up function. You see it's going down, but it's kind of curved upwards. So it's kind of decreasing, but like at a slower rate. And so that's called concave up. This is increasing concave up. So again, it's increasing, but maybe at a slower rate. This is going to be increasing concave down. And this is going to be decreasing concave down. So a lot of times, the way that it's taught is it's kind of used with a smiley face. And so this is the way to think about concave up. So concave up, we're happy. We're happy when it's concave up. So concave up is like this. So if you divide it in half, this is decreasing concave up. This is increasing concave up. It looks like a smiley face. Concave down, we're sad about. So you divide it in half. This is obviously increasing concave down. This is decreasing concave down. So this is concave up, concave down. All right. That's how it was taught to me. That's how a lot of people still teach it. It's just kind of a little trick when you're actually looking at a graph or graphing something and you know, oh, this is decreasing concave up. What does that look like? You can just kind of refer back to the smiley face method. All right. So now we have, oops, sorry. Now we have the formal definition of concavity. So let f be a function differentiable over some interval. That's kind of going to be the case no matter what we do. If your first derivative is increasing, then we have concave up. If your first derivative is decreasing, then we're concave down. So I don't love this definition. This definition is in terms of the first derivative, but concavity isn't first derivative. Concavity is second derivative. And so that I do, in fact, whoop, okay, I saw a little notification on my computer. So if at some point my voice cut out, I'm going to check the recording. I will kind of put in the notes if something came out. I saw that my fiance's AirPods connected to my laptop. So if my voice cut out, it's because my voice got transferred somewhere else and it didn't connect. So if that's not the case, then all good. If it is the case, then I apologize and I will kind of write up kind of what I said, but I could just do a little refresher. So I don't love this definition because it's in terms of the first derivative. So the concavity is actually going to be in terms of second derivative. So I do believe that I have this on another slide, but I want to have it on this slide. So concavity is second derivative. So if your second derivative is greater than 0, that means we're concave up. If your second derivative is less than 0, then we're concave down. There's really not going to be a time that you're going to have to look at this in terms of the first derivative, so I don't necessarily love that definition. Okay, oh, here's the definition right here. So this is going to be the actual definition of concavity. Again, I don't like the formal definition with the first derivative. So if your second derivative is positive, then you're concave up. If your second derivative is negative, then you're concave down. That's the definition we're going to be using when it comes to testing for concavity. All right. Now we do have, obviously similar to maxes and mins, where you have like increasing to decreasing gives you a maximum, decreasing to increasing gives you a minimum. We do have a similar idea when it comes to concavity, when we go from positive to negative and negative to positive. But there's actually no differentiation between positive to negative and negative to positive. All that matters is that you have a change in sign. And so if that's the case, we have this thing called an inflection point. So if f is continuous and f changes concavity, that means it goes from plus to minus or minus to plus, then the point AF of A, so wherever that point is that this occurred at, is called an inflection point. So that just means you have a change in concavity. And this is what it'll look like right here. So if you go from second derivative positive to second derivative negative, you see this is clearly going to be, this here is like the part of the smiley face. You go from concave up to concave down, and right here is where you switch from concave up to concave down. So this is what it means to be an inflection point. And you notice, for example, here and here, you don't have an inflection point because you continue to keep the same sign when it comes to your second derivative. So you're positive, positive, that means that you don't change concavity. As you can see, this is going to be concave up going into concave up, and so nothing changes. So let's go ahead and determine the intervals of concave up and concave down, and we'll list off the inflection points. Again, we're not going to graph it. You can check that if you'd like. So because here we're just asked for intervals of concavity, we are just going to kind of do the first derivative and skip right to the second derivative. Typically, you're going to be asked for everything, though. You want all of the intervals of increasing, decreasing, concavity, maxes, mins, inflection points. This is why it's very important that you're very solid on maximums and minimums, because in this section, you're really just going to be asked for boom, 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 all of the information you could possibly find. And then you'll be asked to graph it all. So let's go ahead and determine the intervals of concavity and if we have inflection points. So if f of x is this guy right here, then f prime of x is 3x squared minus 12x plus 9. But because we're just looking for concavity here, I don't care about the first derivative. The first derivative is only going to be used to get to the second derivative. So the derivative of this is 6x minus 12. All right, and we solve the second derivative the same way we would solve the first derivative. So we want to set it equal to 0 and solve. 6x minus 12 equals 0. So we'll add the 12 over, divide by 6, and we get that x is 2. So we don't necessarily know if that's going to be an inflection point or yet not. An inflection point or not yet. But we can go ahead and figure it out. So we're going to use the same method that we used for our first derivative, which is a number line. And we're going to label it second derivative because that's what we're looking at. So this is our second derivative. And we only have one special point that we're going to be considering. So we only have two intervals that we have to consider, less than 2 and greater than 2. So f of something less than 2, you could choose 1, but I'm going to choose 0 because, again, 0 is just way easier to plug in. Plug in 0 and you're plugging it into the second derivative because that's the function that we're now looking at. You get negative 12, and so that's negative. Negative in the second derivative tells us we're concave down. Concave down. Now I'll choose a number greater than 2, so f of 3. That's 6 times 3 is 18 minus 12 is 6. So this is a positive, which means that we're concave up. So for down, our interval will be negative infinity to 2, not including 2 because the concavity at that specific point will be actually determined. We'll consider this a little bit later. It'll be determined whether we have a maximum or a minimum, what the concavity is at the specific turning point. And then up from 2 to infinity. An inflection point, sometimes we just abbreviate that IP, and inflection point is going to be at 2, but I will actually write it as a point. So let's see here. So if I know that we are looking at x equals 2, f at 2 is, let's see, I have this written down. This is 32. So the inflection point is at 232. All right, this is just going to be a kind of table version of everything that I just mentioned. So if our first derivative is positive, second derivative is positive, then we're increasing concave up and so on. This is, again, the table version of the graphs that we were looking at. So if you'd like to look at this, stop for a second, kind of just review, make sure that everything looks up to par here, go ahead. But nothing is different here than what I've said so far. All right, and again, this is another graph kind of just showing the same thing the table said, the same thing that I've been saying so far. So here's decreasing concave up, increasing concave up, increasing concave down, and decreasing concave down. So these are just intervals to kind of show you exactly what it looks like. And as you can see, this goes from concave up to concave up, so this is not an inflection point, but this, because it goes from up to down, is an inflection point. And in fact, it's the only inflection point in this entire graph. All right, now we have this idea called the second derivative test. Now, I don't typically use the second derivative test because I think it's honestly more work than it's worth, but it's something that's important to note because it might be referenced in like a later course. So the second derivative test says if your first derivative is 0, that means you probably have either a max or a min there. Most likely you might have an inconclusive weird thing going on, but usually it's a max or a min. And the second derivative is continuous. If your second derivative at that point is greater than 0, then it's a minimum. If your second derivative is less than 0, then it's a maximum. So you don't necessarily have to consider it goes from increasing to decreasing or decreasing to increasing. You can just determine it with the second derivative test. If it's 0, you can't tell anything. I do suggest maybe just having this in the back of your mind, but you're going to need to be able to show whether it's a max or min using the number line or using the test points regardless. Like you'll be asked to do that on any like written assignment I give you or really any type of assignment that I give you. It's expected that you know how to do it that way and not necessarily just with the second derivative test. So this is a helpful maybe method to check, but it's not the method that you should be using to actually determine if it's a max or a min. All right, and this is again a little drawing indicating that what we just said was true. So we see here, this is a maximum, which tells us that our first derivative is going to be equal to 0. And at this point, our second derivative is going to be less than 0. And we know that because this is concave down from here to here, we know that it doesn't become concave up anywhere, which means that this also has to be concave down at the point A here, which means that it has to be negative. And the same with B here. This is concave up. Concave up means that our second derivative is positive, which means that at the specific point, our second derivative also still has to be positive. All right, so this will be the last question of today. This is kind of the all-encompassing question. And then in the next lecture, we're actually going to take this, add a couple more steps to it, and then we're going to be able to graph our function just from this. So we're going to find all intercepts, intervals of increasing and decreasing, local and absolute maxima, local and absolute minimum, intervals of concave up and concave down, and the inflection points of this graph. So actually, I don't know if we'll add anything else to this, but we will graph it. The graphing it is honestly kind of the easy part once you know how to do all of this. So what's really important is that you understand what comes from what. So we have to remember intercepts come from our regular old function. So this comes from f of x. Intervals of increasing and decreasing. This comes from f prime of x. Maxima and minima also will come from f prime of x because we do that based on increasing and decreasing. And concavity come from the second derivative, and so does the inflection point. So we're going to need to be able to solve pretty much everything equal to 0. So the intercepts, we know that the y-intercept is when x is 0. So the y-intercept is always the easier one to solve for. That is f at 0. If you plug 0 into this thing, you just get 0. So the y-intercept is a 0, 0. For the x-intercept, we know the x-intercepts are when y is 0, so x cubed minus 6x squared equals 0, and we can solve this function. So what I could do is I could factor out an x squared, and what I'm left with is x minus 6 equals 0. And so I actually get that x equals 0 and x equals 6 are my x-intercepts. This is all we're going to do with the original function. This is really all the original function is good for when it comes to calculus. Now we can use the first derivative to go ahead and determine intervals of increasing, decreasing, and the extrema. So f prime of x equals, so the derivative of x cubed is 3x squared, and the derivative of minus 6x squared is minus 12x. And if I set that equal to 0 and solve, what I could do is I could factor out a 3x, and I'm left with x minus 4 equals 0. And what I get is that x equals 0 and x equals 4. So I can go ahead and now create my number line for f prime of x. And I can plot 0 and 4. And I'm going to have to go ahead and test some points. I'm going to move my face down here. So let's see here. I need something less than 0. So maybe f of negative 1. And I'm going to plug negative 1 into this. And I'm going to kind of use the factored method to make it a bit easier. 3 times negative 1 is negative 3. Negative 1 minus 4 is negative 5. So this will give us positive 15. So this is plus. Between 0 and 1, maybe I'll just choose 1. That's pretty easy. So this is 3 times negative 3, which is going to be negative 9. Right? 3, negative 3, yeah. So this is negative. And then I can choose, say, 5. So f prime, sorry, all of these are f prime. F prime at 5 is 3 times 5 is 15. 5 minus 1 is just 1, so this is just positive 15. So this is positive. So now what I have is we are increasing from, we have 2 sets. So we're going to use our union. We may have seen that when we were talking about domain. We haven't seen that in a little while. So we're increasing here from negative infinity to 0. And we're going to say union because we're also increasing here from 4 to positive infinity. We're only decreasing in one interval, and that's going to be 0 to 4. All right. So what's happening is we can now determine maximums and minimums. So from increasing to decreasing, we know this is going to be a maximum. So max at x equals 0. And decreasing to increasing gives us a minimum, min at x equals 4. All right, so now this is everything that the first derivative will tell us. This is the absolute extrema and increasing and decreasing. Now we can consider the second derivative. So f double prime of x equals, we're going to take the derivative of this function because we don't want it factored out when we actually derive it. Derivative of 3x squared is 6x. Derivative of minus 12x is minus 12. I promise we don't usually get this for a second derivative. This is not like the second derivative. It's just I apparently am bad at making questions that don't have the same second derivative. Sorry. Set this equal to 0, and if we add the 12 to the other side, divide by 6, we get x equals 2. Again, sorry. 2 is not like the number for second derivatives. It's just coincidental here. So we'll create another number line, put a 2 here, label it as our second derivative so we remember, and we can test points here. So now the second derivative at, I'll say 0, because again, it's easier, is going to be negative 12. So that's negative. And then the second derivative at, say, 3 is 6 times 3 is 18, minus 12 is 6. So this is positive, which tells me we are concave down from negative infinity to 2. We are concave up from 2 to infinity. And it tells me that we have an inflection point, and that is going to occur at 2. Let's see here. 2 cubed is going to be 8. So f at 2 is 8 minus 6 times 4 is 24, which is going to be negative 16. So we have an inflection point at to negative 16. All right. We know it's an inflection point because our concavity changes here. So if you have any questions, as always, let me know. It's very easy to go from this to graphing it. This is the absolute worst, most hardest part about any of it is actually getting all of this information before the aspect of graphing it whatsoever. But I'll show you my way of graphing it in the next lecture. That kind of makes it a little bit more cohesive and minimizes room for error. So if you have any questions, let me know, and I will see you for the next lecture.